Organic Chemistry Chem 213, Exam 3 Material, Part 3. Nucleophilic addition reactions of aldehydes and ketones. The most common reaction of aldehydes and ketones is nucleophilic addition reactions. The nucleophile, it can either be neutral or negatively charged, adds to the electrophilic carbon of the carbonyl group from a direction approximately 45 degrees to the plane of the carbonyl group. At the same time, rehybridization of the carbonyl carbon from sp2 to sp3 occurs. So this is the general mechanism when you have a negative nucleophile. The nucleophile will come in and about 45 degrees will attack the carbonyl carbon. And what's going to happen is you're going to form oxygen minus an alkoxy group. And remember, oxygen is fine holding on to a negative charge. It can do that. What this mechanism isn't showing are the lone pairs around the oxygen. You might want to include those. I wanted to go ahead and just show you the general pieces without the dots because sometimes that just kind of gets in the way. So keep in mind when the nucleophile comes in, it's bringing in 2 electrons. It'll give too many electrons to carbon. It only needs to have an octet. So that pair of electrons will go to the oxygen here. So this will actually have 3 lone pairs and a negative charge. And then what's going to happen is we're either going to have water or an alcohol. Remember, this is a general mechanism. And what's going to happen is this is going to be protonated and the hydrogen's going to go there. Or if it happens to be an alcohol, we'll see later that the R group goes there. But this, again, is the general mechanism for negative nucleophiles. So let's talk about nucleophiles. They can either be negatively charged or neutral. If they're neutral, we have to kind of do something to them to want to go ahead and undergo the reaction. The overall charge on the nucleophile is not considered. Basically, what's going to happen is if you have a negative nucleophile, it's just going to pretty much go in there and attack that carbonyl group. So here are some negatively charged nucleophiles and examples of those. And here are some neutral nucleophiles, and we'll be talking about these also. We have water, we have alcohols, and we have ammonia, and we also have amines. And the amines that we're talking about here can be primary or secondary amines. So let's go ahead and talk a little bit more about the aldehyde and ketone and what's going on in terms of the delta and the delta positive and negative. So what's happening with an aldehyde is when you have an R group coming on here, it's going to go ahead and donate a bit of its electrons. Remember, we have electron donating group. And what it's going to do is it's going to have less stabilization than the ketone that has the 2 R groups coming in. So usually we will see that the aldehyde is going to be more reactive than the ketone. And this is also due to steric reasons. So not only do we have in an aldehyde, this one part over here is a hydrogen that doesn't take up much room. Remember, in a ketone, if this is something as, it can even be as big as a butyl group, but that can definitely keep the nucleophile from coming in and actually adding to it. So it can sterically get in the way too. So we have an electronic reason and we also have a steric reason on why ketones are less reactive than aldehydes. So the aldehyde carbonyl group is more polarized than the ketone. As in carbocations, the more alkyl groups stabilize the positive character. And again, a ketone has more alkyl groups, so it stabilizes it, meaning if it's stable, it's going to be less reactive. It wants to stay how it is when it's stable. So now we're going to look at the addition of the neutral nucleophile, water, hydration. Aldehydes and ketones react with water. They're also known as geminal or gem diols. If you remember, the 1,2 diol was a glycol. Well, a 1,1 diol is a geminal or gem diol. You do need to know that group. This reaction is reversible. And the reaction is slow in pure water but can be catalyzed by both acids or bases. And the equilibrium generally favors the carbonyl carbon over the hydrate. So this is the general reaction. In the next couple slides, I have some more specifics. So take a look at this general reaction. What's going to happen is water's going to come in there. It's a hydration reaction, or known as a hydration, because both H and OH are going to be added to our molecule, and HOH is water. So you can see the product here will be forming a 1,1 diol. So let's go ahead and take a look at the relative energies and more specifics here. So equilibrium generally favors the carbonyl compound over the hydrate for steric reasons. It just has more room that way. So acetone in water is 99% ketone. Now it can react with water and it can form the 1,1-diol, but it would prefer not to. And acetone will take water. In fact, when we want to remove water from our glassware in lab, that's one of the things we do. We add the acetone, it'll grab the water, it'll actually form this hydrate, and we can go ahead and have that remove, and that's how it actually removes water when you use acetone to clean your glassware in lab. An exception to this, though, because it says it generally favors carbonyl compound. An exception is simple aldehyde. In water, formaldehyde consists mainly of the hydrate. So formaldehyde, again, one of the smallest of our aldehydes, actually favors the hydride. So we have, again, two competing things. One, the ketone favors the carbonyl, whereas simple aldehydes, the small aldehydes, favor the hydride. Notice the reaction arrows. We have the smaller direction means less favored, the longer direction means the more favored. The addition of HY to carbonyl group. This is when Y is going to be different kinds of compounds, so OCH3, but this could be any alkyl group, so OC could be ethyl, methyl, propyl, all those kind of things. We have an oxygen, so this is O and R basically. OHs, bromide, chloride, and HSO4. So that's what Y could be in this case for all of these here. That could be substituted here. So I'm actually showing you 1, 2, 3, 4, 5 reactions here. Notice that this reaction is favored in the reverse direction, and it's readily reversible. What it's telling us here is Y is electronegative, and what it does is we get an addition product. This is, I think, the first time we see this adduct. What they did was they took the word addition and the word product, well, the two words addition and product, and made it one word, adduct. So if you ever read, and you'll see this sometimes in experiments, and they'll say the adduct it's the addition product. It's a shorthand for that. So this is a reaction that actually prefers the reverse direction, but we can actually put OCH3, OH, Br, Cl, HSO4 in this position here where the Y is, and all of those compounds would go right here, but you'd still have this converted to an OH. Nucleophilic addition of HCN, cyanohydrin formation. Cyanohydrin, that's this compound right here where you have an OH and C triple bond N. This reaction is reversible and also base catalyzed. And what happens is we form the cyanide ion, HCN. The mechanism is we have the cyanide ion right here is negative. This carbon is negatively charged. It's going to be attracted to the carbonyl. Remember, that's slightly positively charged. And we get the intermediate where the pair of electrons go to this oxygen. Oxygen can definitely handle this negative charge here. Carbon is now triple bonded to, this carbon is bonded to cyanide. And don't forget, this carbon here is triple bonded to this nitrogen. We're just not showing it. We have a second cyanide coming in, and what's going to happen, this is also reversible, keep that in mind, and what's going to happen is we're going to go ahead and then put the hydrogen, we're going to protonate this oxygen, and then we form again this ion, which can be used in a further reaction. So it's a reversible reaction, we regenerate this, we can use this again. So this is a classic reaction where it's showing you the nucleophilic addition of HCN, cyanohydrin formation. Cyanohydrins, how do you use them? Well, basically, they're useful because we can use them in further chemistry. What we can look at here, so here they have the cyanohydrin right here. You can go one of two ways with this. You can convert this to 2-amino 1-phenyl ethanol, the specific one with the lithium aluminum hydride. And in fact, if you remember, lithium aluminum hydride is a reducing agent, so we should have more bonds to hydrogen, and that's exactly what happens in my product here. Notice this is C triple bond N. Well, now this C has 2 hydrogens, and this nitrogen has 2 hydrogens, so more bonds to hydrogen. So this was a reduction reaction here. Another thing we can do this is we can add an acid and heat it up, and we can convert it to a carboxylic acid with the OH group. So this could be hydrolyzed to yield a carboxylic acid. So these are two reactions, uses of cyanohydrins. Nucleophilic addition of Grignard reagents and alcohol formation. Treatment of aldehydes and ketones with a Grignard reagent yields an alcohol. We saw this back in Chapter 17, Section 6. Unlike nucleophilic addition reactions of water and HCN, these are not reversible because the carbanion group is too poor of a leaving group. So we can take our carbonyl compound here, the R group that's in our Grignard. Remember how to make a Grignard reagent. It's possible you might be asked to show that. And what's going to happen is the oxygen here, the carbonyl oxygen, will grab the magnesium and the halogen that's here. Under protonation, oh, and sorry, I forgot to mention this, the R group that came in our Grignard is now on this carbon here. And what's going to happen under protonation is going to convert this to an alcohol. So whatever you have here as your R group, those are more carbons you're putting on here. So if you remember back from section 17.6, we talked about converting or making, how do you make alcohols? Well, we talked about formaldehyde. When you want to make a primary alcohol, you have to start off with formaldehyde. And so if you're making a primary alcohol, let's say it has 6 carbons, then your Grignard reagent has to have 5 of the 6 because you can only use formaldehyde here. Other aldehydes form secondary alcohols and ketones form tertiary alcohols. So again, we've seen this before. This is actually repeating what we saw back in Chapter 17. Hydride addition, we're going to convert our carbonyl group to an alcohol using a reducing agent. And here we have lithium aluminum hydride or sodium borohydride, where they react as donors. Carbon has 2 bonds to oxygen, no bonds to hydrogen. The reducing agent, either of these two, is going to contribute a hydrogen and to the carbonyl carbon. Remember, we're going to get oxygen with its minus charge. We talked about we're going to see this a whole bunch of times with carbonyl groups. And then it's going to go protonation, and now we have, instead of carbon having 2 bonds to oxygen, none to hydrogen, we now have 1 bond to oxygen and another bond to hydrogen. This is a reduction reaction. Nucleophilic addition of amines, imine, and enamine formation. So let's take a look at this reaction here. We have our aldehyde or ketone. This compound right here, RNH2, this nitrogen here must have, for this reaction to go, 2 hydrogens. So in order for an imine, this is the structure for an imine. Be sure to add that to your functional groups. In order for this reaction to happen, you have to have 2 hydrogens. So this only works with either a primary amine or ammonia, because these 2 hydrogens have to leave for this nitrogen-carbon double bond to happen in an imide. Now, taking a look at the ketone or aldehyde in this direction. Oh, and I want you to notice, nothing happened on this side. All the action happened on the carbonyl group. All right, what's going to happen if we happen to use, in this case, if we happen to use a primary, secondary, or even ammonia, we can actually, it has to have 1 hydrogen available to leave. What's going to happen is we're going to put the nitrogen where the carbonyl carbon was. Notice these, it only needs 1 hydrogen. This, remember, this does not work with tertiary, but it could be ammonia, primary, or secondary it works with. But what happens in this case is we actually get a carbon-carbon double bond, and we get an amine here. So take a look at this. Do you see the EN piece right here? That's referring to the double bond right here. And the amine piece right here refers to the amine piece right here. So that is the general structure of the group N-amine versus an imine. And I also want you to notice in this reaction that they are both reversible. Again, this side has to have at least 2 hydrogens, but it can have 3. This side has to have at least 1 hydrogen, but can have up to 3. Nucleophilic addition of hydrazine, the Wolff-Kishner reaction. So this is a named reaction. The treatment of an aldehyde or ketone with hydrazine, that's this, 2 nitrogens and 2 hydrogens on each side. Remember, nitrogen has 3 bonds, so there'd be a single bond between these guys. Also, we would use potassium hydroxide, converts the compound to an alkane. So we're able to take an aldehyde or ketone, and we're able to convert it to an alkane. So is this oxidation or reduction? Well, we have 2 bonds to oxygen here. We have no bonds to oxygen, 2 to hydrogen. This would be a reduction reaction. And remember, we talked about the fact that your reducing agents tend to have a lot of hydrogens in them. So you can kind of see a bunch of hydrogens in there. So here is an example reaction. I have an aldehyde. What's going to happen to this carbonyl carbon is it's going to become an alkane. Nucleophilic addition of alcohols. So we're going to have 2 moles of alcohols in this case. This is going to have an acid catalyst. This reaction is reversible. And what we're going to do is our aldehyde or ketone will form an acetyl group. Acetyl is when you have 2 OR groups on the same carbon, acetyl. So again, add that to your functional groups that you need to know. 2 equivalents of alcohol are present in order for this to happen. The acetyls, we can actually use those as a protecting group for aldehydes and ketones. So what we can do is we can convert our aldehyde or ketone to an acetyl, which is less reactive. It can undergo other kinds of reactions, and then you can go back and reverse and get your aldehyde or ketone back. If you start off with an aldehyde, then what you form is an acetyl. If you start off with a ketone, then you form what's called a ketal. So to look at the formation of acetyls, this is where I'm going to show you where the 2 moles of alcohol come into play. So we have our, in this case, it's showing you 2 R groups. So this could be an aldehyde or a ketone. And over here I called it an acetyl, so technically I guess this would be an aldehyde. So you have your alcohol coming in here, and notice I also have CH3OH happening here. H plus catalyst. This, what's formed here when you get the first one on there, is known as a hemiacetal. So hemiacetal is when you have 1 OR group on there and you have an OH group on there. So the second mole of alcohol is going to come in here. Again, the same conditions, hydrogen catalyst, and then we will form the full acetyl. So it's hemiacetal and then the acetyl. So it takes 2 moles of alcohol in order for this to happen. Alcohols are weak nucleophiles, but acid promotes the formation, helping with the conjugate acid of the carbonyl group. Addition yields a hydroxy ether, known as a hemiacetal. This is also reversible, or a further reaction can occur. And the last step is the protonation of the OH, and loss of water leads to an oxonium ion, to which a second alcohol can form the acetyl. All right, the nucleophilic addition of phosphorus Ylide. This is also known as the Wittig reaction. We do have a lot of named reactions in OChem, and here's another one. So what is actually happening in this reaction is we are converting our carbonyl group, C double bond O, to an alkene, C double bond C. We're going to be using triphenylphosphine. That's 3 benzene rings attached to this phosphorus. In this case, we're showing it in the form of having the phosphorus having its octet with its lone pair. And the lone pair is going to attack, in this case, our CH3 group on our bromomethane. And in an SN2 substitution, because this is a primary, we're looking at a primary alkyl halide here, what's going to happen is our phosphorus is going to get a positive charge here, and the CH3 is going to be attached to it. And then we bring in our butyl lithium, and we also have our THF, our tetrahydrofuran. And now we have this phosphorine compound. This is how the compound is made that we're going to be using. Next slide. We're actually be using that compound in our reaction. So here we go. This is that compound we just saw made. Now we have 3 benzene rings on this phosphorus. So this is kind of a shorthand notation of showing that phosphorus. Remember those benzene rings. pH is a shorthand notation for that aromatic ring. We've seen a lot of examples of benzene in the shortcut way of writing it. So this is this whole compound. I'm going to go back one more slide, guys. So this right here is what we're talking about using here. We have phosphorus with its 3 benzene rings, and we're going to abbreviate that on the next slide as pH. Do you guys see that? All right, so what's going to happen is this carbon right here, it's a carbanion, is going to attack this carbon. And then the pair of electrons are going to go to this oxygen with a negative charge. We've seen that before. So we have this carbon now bonded here. And this oxygen here, negative oxygen, is going to be attracted to this phosphorus. And it's literally going to bond from this oxygen to this phosphorus. So we have this square bond happening. Really bad bond angles. We have 90-degree bond angles. It doesn't like that. So what is it going to do? It's going to end up causing this whole piece right here is going to remove, and a carbon-carbon double bond is going to form here. So this whole piece is going to get out of there, and we regenerate this phosphorus with its 3 benzene rings and now an oxygen on there. So this is the mechanism of the Wittig reaction. Again, one of the unusual things that happens is this right here. We have a cyclo of 4 elements, or 4 different well, we have actually 3 different elements, but we have a cyclobute happening here. Very unhappy with that bond angle. Something's got to go, and this large piece here is going to get out of there. The uses of the Wittig reaction. It can be used for monosubstituted, disubstituted, trisubstituted alkanes, but not tetra. What do we mean by that? So as a reminder, when we have our carbon-carbon double bond, remember, we can have on our alkene, we have 4 different R groups that could be up to 4 different R groups that can be on there. So monosubstituted would be 1 R group with 3 hydrogens. Disubstituted, it could be disubstituted would be 2 R groups with 2 hydrogens. 3 would be 3 R groups, 1 hydrogen. But it's telling us that tetrasubstituted can't happen. So if I have no hydrogens here, 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 or here, just all carbons, not going to happen. All right, so for comparison, this is a reaction of the Wittig reaction, and that's this bottom one here. If I have cyclohexanone and I want to go ahead and make a compound where I have the carbon-carbon double bond coming off the ring here, when I use the magnesium, I use the Grignard reagent, what's going to happen is I'm actually going to get a mixture of products. I'm going to have the carbon double bond on the ring itself, or I'm also going to have it coming off of here. And this is a 9-to-1 ratio, so only 10% is what's going to happen here. But if I do this reaction and I use the Wittig reagent, basically what's going to happen is I can almost guarantee it's 84% I'm going to get this product. So what this could be used for is for us to have a more specific product, if we're looking for one in this case, where I have the carbon-carbon double bond on this part here. The Cannizzaro reaction, biological reductions. So we take a look at this reaction here. I have an aldehyde. It's going to undergo a reaction with OH, and this will be converted to a carboxylic acid. Plus, I get a mixture of products where I also have an alcohol here. So this is the Cannizzaro reaction. It's a reduction in biology. The reaction takes place by nucleophilic addition and has few practical applications. The adduct of an aldehyde in OH, so adduct meant addition product, can transfer hydride ion to another aldehyde, resulting in a simultaneous oxidation and reduction. But basically what I would like to do in this mixture of products is I would like you to name which product was oxidized, or actually label which product was oxidized and which one was reduced. All right, this one has 2 bonds to oxygen. Now it has 3. That was oxidized. This has only 1 bond to oxygen. This product was reduced. So that's one way we can make this more practical, is by practicing identifying our oxidized products and reduced products. Conjugate nucleophilic addition to alpha-beta unsaturated aldehydes and ketones. So we have some new things we need to take a look here. Alpha-beta unsaturated aldehydes and ketones. So let's see what that means. A nucleophile can add to the carbon-carbon double bond of an unsaturated, or an alpha-beta unsaturated aldehyde or ketone. So I want you to see what we're talking about in an alpha-beta unsaturated ketone. So come down here. Let's take a look at here. This one's labeled pretty nicely. All right, see this carbon right here? This is our carbonyl carbon. Right next door to it, it could be left or right, but they're only showing us one side of it. Right next door to that is the alpha position. When you have your carbonyl group here, right next door is the alpha. Working away from that would be beta, and then it keeps on going on. We'll be seeing those notations later. Gamma would be next. So let's take a look at this terminology. It says alpha, beta, unsaturated aldehyde or ketone. Unsaturated means we're going to have some sort of multiple bond. So do you notice between this alpha and beta I have a double bond? And then right here I have either an aldehyde or ketone depending on if I have an H here or an R group here. This is the general structure here of an alpha beta unsaturated aldehyde and ketone, and we're going to see these a lot more this semester. All right, so what this slide is doing is it's comparing the direct 1,2 addition versus the conjugate 1,4 addition. The direct 1,2 addition, the nucleophile will come in, it'll attack the carbonyl carbon, it'll force that pair of electrons to go to that oxygen, causing this negative charge, remember that? And then we're going to protonate it with the OH. So this is the direct 1,2 addition. We've seen that with negative nucleophiles. That's the general reaction. Well, what can happen if you happen to have a ketone or an aldehyde that also has an alpha beta unsaturated situation? Take a look at this. Instead of the nucleophile attacking the carbonyl carbon, the nucleophile attacks the beta carbon. The nucleophile is going to be bonded to the beta carbon. This tells me the pair of electrons, instead of a carbon-carbon double bond here, the carbon-carbon double bond is going to go here, causing these electrons to go up here and give us that anion, the oxygen negative. So right here, we have, this is the result of this happening here, and what's going to happen is going to be a shift. We're going to have a shift happening. Remember, this oxygen really doesn't want to have a negative charge, and what it's going to do is it's going to throw its electrons down here. This is going to become an enolate ion, and notice this is resonance between these two. This is our resonance arrow. So we're going to have a resonance happening between this form and this form, and that means it's going back and forth, right? Remember, my electrons are flying back and forth. So in one format, I'm going to have a negative charge oxygen here. In another format, I'll have a carbanion here. Well, while this process is happening, remember my nucleophile is on my beta here. What's going to happen is protonation is going to happen, and when it protonates, it's going to protonate this carbon right here, my alpha carbon. The alpha carbon will get a hydrogen. So what happens? The difference between a direct 1,2 addition or when my ketone or aldehyde is an alpha beta unsaturated is my nucleophile goes on the beta position here. The carbonyl group remains the same, versus if I don't have that, then the nucleophile is going to now take the carbonyl carbon and it's going to attach directly to that. So that's the difference between the direct 1,2 addition or if my aldehyde or ketone has the alpha beta unsaturated situation. Conjugate addition of amines. Primary and secondary amines add to alpha beta, there we are again, unsaturated aldehydes to yield beta amino aldehydes and ketones. All right, 3-butene 2-one. This is a ketone, ONE ending. My ketone features on number 2. I have a double bond starting on carbon 1, 2, 3. This is an alpha beta unsaturated ketone. Now this nitrogen here needs to be either primary or secondary. Tertiary won't work. Tertiary won't work because it has to have this hydrogen available to leave on this nitrogen. And what's going to happen is this nitrogen is going to attach to the beta position and the double bond's going to go away. So let's look over here. This was our alpha, this is our beta, there's my nitrogen. And remember, only one hydrogen has to be there, so it could be primary or secondary. They gave you a secondary example. This won't happen with tertiary. And notice the attachment point is this nitrogen to the beta position, double bond goes away. All right, let's try this on your own. So this again is an alpha beta unsaturated ketone. It just happens to be on a ring. So let's check. Does this amine have an available hydrogen? Yeah, in fact, it has 2 available hydrogens. Only one's needed. So this nitrogen is going to attach where? At the beta position. The double bond's going to go away. Notice my nitrogen is at the beta position. Double bond's going to go away. Now my nitrogen is attached at the beta position. So this is a conjugate addition reaction of amines. A primary or secondary amine is needed. And what's going to happen is my amine is going to attach to the beta position, double bond goes away. Conjugate addition of alkyl groups. On this slide, it's one of those interesting situations. I kind of think that the slide should be in reverse order, but let's just go ahead and take a look at the whole slide so you can see where I'm coming from in this case. So I actually want you to look at the bottom here. This is the Gilman reagent. The Gilman reagent is another organometallic, and in this case we have an R group and X. X is any kind of halogen that makes a great leaving group. 2 moles of lithium and pentane, and what happens is we end up getting our lithium attached to our R group. It basically substituted where the halogen was. Now what's going to happen is we're going to take 2 of these, notice I have 2 moles here, and we're going to introduce copper iodine and ether, and now we made this compound right here. This is a lithium diorganocopper. This is our Gilman reagent right here. This is our Gilman reagent. So again, this is where I think the slide should be reversed, is because here's how we make it, and up here we're going to use it. So again, I want you to see that this is how the Gilman reagent is made. Up here is where we're going to use it. So again, I want to show you the whole slide right off the bat because I think this should be in the other order in my head. All right, so let's take a look at this reaction. Are we all good with where this came from? Remember, it came from right here. This is how it was made. Just like we had to make some other reagents, this is showing us how to make the Gilman reagent. All right, so now let's use it. This is the reaction of an alpha beta unsaturated ketone. This reaction does not work with aldehydes. And what's going to happen is this R group here in our Gilman reagent, and in fact, I want to show you that it's the same R group in the very first step here. It's the same R group. All right, so this R group right here is going to attach to the beta carbon, and the double bond's going to go away. So this is a reaction where we can put an R group on the beta position. This double bond goes away, and it only works with ketones, not with aldehydes. So again, down here, the second half of the slide shows us how we made this, what we use up here at the top. So here we're going to show you the mechanism of how it does it. So we have our lithium, our copper, and our 2 R groups here. And really what attaches to the beta carbon is actually going to be the copper itself. The copper is going to be attracted to it first. So our copper is going to be attached to this carbon. So when it bonds to this carbon, that's too many bonds to too many bonds to this carbon. So this pair of electrons go here, and that pair, and this is too many electrons to this carbon. So that pair of electrons come up here. So that's where this minus charge comes from. And then what's going to happen is we're going to get the copper is actually going to, this is a single arrow here, so it's not reversible. It's showing us that this copper here is actually going to move away, and one of the R groups is going to be in its position, giving us RCU left over. And then the protonation, the last step, is going to happen that causes this double bond, this hydrogen right here is going to go on the alpha position, and we're going to regenerate our carbonyl group here. So the primary, secondary, tertiary, alkyl, aryl, and alkenyl. This is something we really haven't seen. This means double bond groups can react, but triple bonds can't. Conjugate nucleophile addition of a diorganocopper reagent, we also get an enone. And the transfer of the R group and elimination of a neutral organospecies, the copper with the R group right here. So this is going to be what happens is technically it's the copper that adds first, but the net result is that R group is at the beta position, double bonds gone. Biological nucleophilic addition reaction. One pathway to amino acids is from the nucleophilic addition of an amine to an alpha keto acid. All right, ready for this one? Alpha keto acids. What we have here is an alpha beta unsaturated ketone again. This is a specific reaction to make amino acids, so that's why they're showing you the two hydrogens on here. What's going to happen is one of the hydrogens is going to go away, and this nitrogen is now going to be attached to the beta position, and the other hydrogen that's now gone is, well, not gone. That other hydrogen that was from here, because I told you this had to have one hydrogen available to happen, it actually goes at the alpha position. So this reaction to make amino acids is we're going to take an alpha beta unsaturated ketone, and we are going to make an alpha keto acid. So alpha, this is our alpha position. This is a ketone. So what do you think alpha keto acid means? Something that's an acid has a hydrogen available to leave. This is an alpha keto acid. This hydrogen here is acidic. It can leave. That's what they're calling this group right here, an alpha keto acid. Remember, this is the first position, or this is the carbonyl group. First carbon away is the alpha, then the beta. So this is an alpha keto acid is what's formed. This is a reversible reaction. Spectroscopy of aldehydes and ketones. So we have a pretty good peak for aldehydes and ketones for the carbonyl group. We can see that at 1600 here, between 1660 and 1770. We've seen this carbonyl group with a bunch of different kinds of compounds, so be sure to look for that group. That's one of its big identifiers here. Aldehydes will also show a characteristic carbon-hydrogen absorption at about 27, 30 to 28, so that would be right in this range here. So pretty much the carbonyls, the first thing you're going to see, this one here, depending on what other functional groups you have, you may or not be able to see that. But again, that's something you should look for. If you know you have an aldehyde, look for this here. If you know you have a carbonyl, look for this one here. Now, IR can get pretty specific if you have a much better system for measuring it. And what we're looking at here is we have some absorption different values based on the different aldehydes and ketones. And so if you were looking at an IR spectrum in more detail, you can actually identify the differences in these different kinds of aldehydes and ketones. For the purposes of this class, you don't have to know all the specifics of all these, but I do want you to know where the carbonyl group is and where that other acetyl hydrogen is. Be sure to be able to label those. NMR spectra of aldehydes. Aldehydes have the acyl hydrogen. That is going to be way down here at about 10. Remember, ketones don't have that. So this is something that we're going to see in our proton NMR for an aldehyde that you do not see for a ketone. And we've got this one, they colorize this. They've got this in pink. We have 1, 2, 3, 4. The signal's split into 4 peaks, which means it's next to 3. And then if you take a look at these hydrogens here, the signal is split into 2. So it's split into 2, so it means it's next to 1 hydrogen, and that's exactly what's being shown here. Hydrogens on the carbon next to the carbonyl group, so that would be the alpha position here, right? Alpha carbons tend to be about 2. They are pulled further downfield. And then we actually have methyl ketone protons are closer to a 2.1. Oh, I want to mention also relative abundance. Do you guys see the height of this versus the height of this? So this is about 1/3 of this. So if you have an integrating line, instead of telling you how many hydrogens, if you take a look, this actually goes up, on the grid, 2 squares? And this goes up about 1, 2, 3, 4, 5, 6 squares. So you have a 2 to 6 ratio, which is actually a 1 to 3 ratio. And that tells me this is 1 hydrogen causing this signal, and this is 3 hydrogens causing that. So keep in mind that integrating line can tell you how many hydrogens we are talking about. With carbon NMR, we have that carbonyl signal pretty high up at 219. So that is going to be a good identifier. There's pretty much nothing else that's that high. So between 190, 215, look for that carbonyl group. Again, we can get, with better instrumentation, we can get much better readings on each of these carbons. So kind of take a look at these numbers, get a feel for them. If something is closer to the oxygen, it should be pulled further downfield. This is a carbon NMR. Notice the noise on the bottom here and also the numbers on the bottom. So you can definitely recognize right off the bat if it's a proton NMR or a carbon NMR. With mass spectrometry, the McLafferty rearrangement is one of the #1 things you do need to know. In fact, there's a couple of things that happens in mass spectrometry. Remember, we've got our molecules in there and we're bombarding them so they break down to fragments. Well, they don't always just break down to fragments. Sometimes they react and rearrange and do all sorts of stuff. So, McLafferty rearrangement, be sure you know how to draw this reaction. What's going to happen? Take a look at this. We have our carbonyl carbon here. Here's our alpha position, beta position. We've talked about those already, but now take a look at this gamma. Alpha, beta, gamma. We have a hydrogen on our gamma position. All these atoms here are going to be involved in a rearrangement. So take a careful look at what happens during the McLafferty rearrangement. You're going to get this piece here. So it's this piece here that's going to be expelled. It's going to be given off. And then we'll have this piece here left over. That's this section here, but it also grabbed this hydrogen. Did you guys see that? Well, of these two pieces here, only one can be detected. Remember, when you have spectrometry, when you have mass spec, what happens is only the positive cations can be seen. So you'll have a peak at this molar mass, but you'll have a fragment loss of this molar mass. So keep in mind, you might be asked which fragment can be detected, but also that's going to help us know what kind of fragment loss we're looking for. Mass spec is a nice way to put together structural pieces based on not only what peaks we have, but what losses we have. Another thing that happens in mass spec when those atoms are being bombarded is we get what's also known as alpha cleavage on our aldehydes and ketones. So what happens, remember this is our carbon, this is our alpha position, the cleavage, the breaking of it happens between the carbonyl carbon and the alpha carbon. It splits it right here. What's going to happen is the carbonyl group is going to have the positive charge. That's the fragment that will be detected. That's where you'll have a peak. You'll have a fragment loss, though, of this molar mass. So as a summary, I want you to remember in mass spec, when we have aldehydes and ketones, you do need to know how to write out the alpha cleavage. If I give you a specific aldehyde or ketone, be sure to put the specific ones in here, not R groups. And so it would be mass spec. You need to know about alpha cleavage. And you also need to know about the McLafferty rearrangement. Be sure to practice drawing these. These are big topics when we talk about mass spec and aldehydes and ketones. And keep in mind, in the McLafferty rearrangement, you have to have a pretty big compound here. Look, 1, 2, 3, 4 carbons have to happen. You're not going to have the McLafferty rearrangement if you have something less than 4 carbons. Not going to happen. It has to have 4 carbons.